Welcome back, guys. We're going to do our second installment of our thermochemistry lecture. So you can see the answers are right there, and I am going to show you my work for them. Oh boy. So, hopefully we can see this, but the equation you're going to use is Q equals mc delta T. Your first step is to convert the moles that I gave you into grams because we're talking about mass, and mass is grams. So in order to do that, in order to do that, you need to take your 1.4 moles of water, in this case the liquid water, because moles is on top, needs to go on bottom to cancel out. So you're going to multiply by the molar mass, which is 18.02 grams, to get 25.2 grams of water. We know our C, because that was given to us, is 4.18 joules per gram degree C. So then our next step was to calculate our change in temperature, or delta T. So you have to take the final minus initial, which was 10 minus 100 to give us negative 90. And then you just plug it all into the equation. So you're going to take your mass times your delta C. Your mass times C times delta T. And we're going to get the answer of negative 9,480 joules. And then we needed to compare that to it as a gas or steam. So we're trying to figure out our Q for steam. Same process, take your moles and convert it into grams in the exact same way we did before. So multiplying by molar mass to get 25.2. Our C was given to us, and that was 1.87. And then our delta T, same thing. We need to take final minus initial, so 110 minus 200 to get, again, negative 90. So because these two states of matter are the same substance and they're changing the same amount of temperature, so negative 90 degrees Celsius, you can compare the Q's. So when we plug in for steam, our equation Q equals mc delta T, you should get negative 4,241. So what all of this means is that for liquid water compared to gas water, it'll take more heat or energy to change the temperature. If you have any questions on how I got any of that or where it all came from, please don't hesitate to send me an email or comment or anything like that on our Google Classroom. All right. So now we're going to talk about this property called enthalpy, which is represented by capital H. It's a type of chemical energy, and it's sometimes referred to as the heat constant content. The Q for reaction will equal the change in enthalpy, or delta H. So the H of the products minus the H of the reactants. But this is if we're at a constant pressure. So then you can get your endothermic reactions and your exothermic reactions again. Q or delta H being greater than 0 means endothermic. If Q or delta H are less than 0, then you've got an exothermic reaction. So heat being released in exothermic or gained in endothermic by the system specifically. When we are writing thermochemical equations, you need to write your complete and balanced chemical equation like we always do, but you also have to include the delta H for that reaction. So for example, we're going to look at this NH4NO3. When it decomposes into NH4 plus NO3, your whole thermochemical equation is down here. So we've got the whole equation. Notice it's a 1:1:1 mole ratio, but the delta H for that would be 28.1 kilojoules, which we can figure out by experimentally by taking 1 gram of the NH4NO3 and actually decomposing it and figuring out what that temperature change is, and then using Q equals mc delta T to figure out what the Q is. And again, because Q and H are equivalent under a constant pressure, then you can say that if the Q is 351 joules, our delta H is 351 joules. So because we're talking about an equation and not a specific amount of it, then you have to convert from the grams that we used into moles. So you would multiply by that molar mass to get 28.1 kilojoules. It is important to note, however, that the sign of delta H will indicate whether the reaction at a constant pressure is endothermic or exothermic, so we should already know that by the positive or negative sign. And when you interpret thermochemical equations, the coefficients, again, remember they represent the number of moles of that substance. Additionally, the physical state and matter of the species, so all the things that you're using or are in the beaker, have to be specified because there are going to be differences between those states of matter, just like what we saw with our liquid water and our steam when we were calculating it. Those had different specific heats because gas versus liquid have different properties. The magnitude of delta H is going to be directly proportional to the amount of reactant or product. So delta H for a reaction is equal in magnitude but opposite in sign for a reverse reaction. So what that means is if we're going from products to reactants and it's positive and you reverse that reaction, so going from products to reactants, it'll be negative, but the amount won't change. The value of delta H for a reaction is the same whether it occurs in one step or a series of steps. This is what we call Hess's law. So if you were going to calculate that, all you'd have to do is get the delta H of each step and then add them together to get that total delta H. So this is going to be our second stopping point here with this knowledge check number 2. The Bunsen burners in our lab are fueled by natural gas, which is mostly methane, so we're going to assume it's pure methane. The thermochemical equation for the combustion of methane is as follows. CH4 plus 2O2 will yield CO2 plus 2H2O. The delta H for this reaction is negative 890.3 joules. So calculate the delta H when you have 5 grams of CH4 or methane reacting with an excess of oxygen. So that should indicate to you that methane is going to be our limiting reactant because we have a whole bunch of oxygen, so that will not come into play. Again, post your answers in our Google Classroom and we'll continue tomorrow.